I am going to talk about endocrine disrupting compounds, but I want to put it in the context of where the world is today. We know there's a carbon problem, right? Any sentient being on the planet who's paying attention to science knows that there's a carbon problem. And I know several people in the room here are working hard to reduce it. That's the outer world, the world of the atmosphere. We also have a problem in the inner world, what Martin was talking about. We have a problem because among those 95,000 chemicals that are in commerce today, some of them can interact with our genes, turning the genes on at the wrong time or preventing them from turning on at the right time. And if you want that fetus to develop healthy, to become a healthy adult, those genes have to behave the way they're supposed to. If genes are turned off at the wrong time when they're needed, or on when they aren't needed, then you set the fetus off on a course of development that can undermine its health throughout its lifetime. That's the key story of what I'll be talking about today. It's not just me saying this. The World Health Organization this year issued a report on endocrine disrupting chemicals saying that EDCs are a global public health threat. Global public health threat. And in fact, a report from the reinsurance industry's CRO forum, Chief Risk Officer Forum, chaired by a Zurich resident, David Cole, who is the Chief Risk Officer for Swiss Re. They issued a report about a year ago that basically said the highest risk for the insurance industry emerges from the probable link between low-level EDC exposure and bodily injury. This is Swiss Re saying this, the CRO forum. We recommend to minimize the use and release of EDCs, and we encourage the removal of EDC micropollutants from wastewater and drinking water, taking into account the individual circumstances of the companies being insured by the companies, by the insurance companies that the reinsurance industry insures. This is a big deal. This is sending signals into the investment marketplace that says companies have to pay attention to their financial risks to the use created by their use of endocrine disrupting compounds. So what is EDCs? Well, Martin summarized it very succinctly. This is a definition from the Endocrine Society. The Endocrine Society is the association of scientists and medical practitioners who, if you have a hormonally related disease, that's who you want to see. 15,000 scientists and physicians around the world. They say that they identify an EDC as an exogenous chemical, something that isn't naturally found in your body, or a mixture of those chemicals that interferes with how hormones control gene expression, turning genes on and off. That's the key role of hormone signaling, not the exclusive role, but that's a lot of what's happening trillions of times a second in your bodies throughout your lifetime. Genes are being turned on and off through hormonal signaling. So, there's that set of chromosomes, the spark happening where the gene is being turned on. The reason why the World Health Organization issued that finding that's a global public health threat is if you begin to look carefully at the huge amount of science that has been published over the last 20 years, focused on how endocrine disrupting chemicals interact with animals and people, you find that this suite of today's epidemics that people are experiencing are tied by that science to varying degrees of certainty. In some cases, it's pretty clear. In other cases, it's much less clear. But those are today's modern epidemics. And there's plausible science saying that endocrine disrupting compounds are contributing to those disease burdens. And none of them is it going to be 100%. Some of them, so the science will probably tell us in the end that actually we got it wrong and that it wasn't involved. But most of those are going to stay on the list. What did the WHO report say? Well, it said first that many endocrine disorders, like that list, are on the rise, far too rapid to be a result of evolution or changes in the frequency of genes. There are about 800 chemicals that careful study has shown to be endocrine disruptors. And as Martin showed, most chemicals have not been tested for most health endpoints. So the list could be quite a bit larger than 800. We know that exposure to both people and wildlife is ubiquitous. There's not a living organism on the planet that doesn't carry some burden of endocrine disrupting compounds. It's because, as Martin said, they're in lots of products and they move. The atmosphere transports them. Water transports them. There is a huge body of scientific literature based on laboratory studies with animals, studies with wildlife, and studies of people, epidemiological studies, that show that are consistent with endocrine disrupting impacts on human health. Because of factors like what Martin mentioned, that most chemicals have not been studied, the estimates we currently have about how much of the disease burden may be due to endocrine disrupting compounds is probably a significant underestimate. Every time we look at a new system, at a new chemical, we find something we didn't realize. There will be a paper coming out in a couple of weeks, for example, calculating the proportion of childhood obesity, the disease burden of childhood obesity that can be tied to one specific endocrine disrupting compound. It will be coming out in a few weeks. And the number is, this is in the United States, the number is big. The good news, and I think there's really good news. Here we have this wave of epidemics. The good news is that the science we have in hand today is giving us guidance for how we can reduce those disease burdens if we act on that science. Okay? We have to act on it. We can't just let it sit in the shelf. We've got to figure out how to use it. So why my focus on EDCs? Well, there are three things. The exposures that can be measured in everyone in this room today are sufficient, based on animal studies, to cause adverse effects. Each of us differs in our susceptibility by, science says, somewhere between 50 and 100-fold. So not everyone is falling down and dying. Not everyone is suffering from portions of those disease burdens. But what is in people today, what the U.S. Centers for Disease Control measures every year in people, shows that levels are sufficient to be of concern. As I said, virtually every living organism on the planet is exposed. But again, for me, the big deal is this huge opportunity this new emerging science is giving us to prevent exposures, and by preventing exposures, to prevent disease. So how can we be exposed to EDCs? There are lots of pathways. Common consumer products, as Martin mentioned, things as prosaic as shower curtains contain phthalates, non-stick frying pans, couches, furniture, in which you, because of California law in the US, have to have a whole lot of flame retardants put on, electronic consumer goods. Pesticides are a whole other route of exposure, from the drift that takes place when they're sprayed and they volatilize into the atmosphere and are spread by air currents, to actual consumption directly in the food that is the produce and the corn and other products that are grown using pesticides, and also from exposure via the movement of the pesticides in the water downstream into the water supply and into drinking water. And very few drinking water cleaning operations have been designed to remove these compounds from drinking water. So if it's in the input, it's in your drinking water. There are many unexpected sources. How many of you know, for example, that thermal paper, those receipts that you get from the ATM machine, those are coated with high levels of bisphenol A, which is a potent endocrine disruptor. And I can explain why it's there. It makes absolute sense to a chemist why it's there, because it's what makes the technology of thermal paper work. But who would have thought that every time you pick up a piece of thermal paper, you're getting BPA on your fingers? I have a friend who's about to publish a study asking what does that mean in terms of input, particularly if you're at a fast food joint, you have your receipt, you pick up a French fry, it's greasy, the French fry, your fingers then are greasy, you get BPA in massive doses. BPA is used to line food cans. 80% of food cans in the US market, I don't know about here, but in the US market, 80% are lined with a endocrine disrupting compound that leaches into the food in the can. Our wonderful effort at recycling, which includes paper, those thermal paper receipts, puts BPA into the recycled paper stock, so that pizza cardboard, recycled cardboard used for pizza boxes contains BPA in it, capable of leaching into the pizza because that pizza is really greasy. And finally, many antibacterial products based on triclosan. Triclosan is a endocrine disrupting compound in addition to being an antibacterial agent. So how could we be in a situation like this? How could something like that happen? Well, you think about how the chemical enterprise works. It's not the chemist's job to figure out what's poisonous. That's not their job. They make things to meet certain material characteristics that manufacturers want. Okay, that's their job. They then leave the identification of toxicity to people downstream. As Martin said, many materials, many chemicals don't require safety testing before they go on the market. Those that do, a lot of the safety approaches are deeply flawed. So there are, as Martin said, there are thousands of untested products that are out there in the marketplace. And it's only as the science of modern molecular genetics and what's called epigenetics and endocrine disruptors have advanced that we realize the scale of the mistake that we've made. It's a big mistake, and how do we walk back out of it? Briefly, what are some common EDCs? Bisphenol A, used in thermal paper, used in line cans, used to make polycarbonate plastic. It generates $700,000 an hour in revenue for the industry. It's a big product. It pays for lots of lawyers. Multiple phthalates, that's a product of chemicals that soften hard plastics or that are actually used in cosmetics to make them, the cosmetic stay on your skin longer. Many types of flame retardants, this is a specialty of Martin's, particularly the polybrominated diphenyl ethers, are widely used to make sure that something doesn't burn in your house when it really wasn't going to burn in the first place. There's a fascinating long series in the Chicago Tribune written last year, which won a major journalism award in the US, all about how the industry has completely misrepresented the science on the way that you really don't need polybrominated diphenyl ethers. The perfluorinated compounds are very common. They're used to make non-stick pans. They're used to make Vortex cloth. They are incredibly persistent and they interfere with gene expression. The organotins have emerged, they're used as fungicides and put in lots of different consumer products, also as pesticides to treat against fungi. Turns out they turn on a gene that makes stem cells, which we all have, stem cells which we need because normally they get a signal from a hormone that turns on a specific gene that causes that stem cell to grow up to be a bone cell. The gene is called PPAR gamma. Well, when organotins hit that gene, they become a fat cell. And you get more fat cells. And that increases your risk to obesity. Atrazine, made by a Swiss company. I'll talk a little bit about later, but it's one of the most widely used herbicides to kill plants in the world in crop agriculture. Roundup, famous for its use in GMO agriculture. Actually, it's really great to kill plants by attacking plant enzymes, but they forgot to tell us that it attacks the retinoid signaling system, which leads to birth defects in invertebrates. And then the classic things, EDCs, the PCBs, other banned persistent organic pollutants, which are so persistent that they're in every one of you today. So I wrote this book with 2 other people in 1996. At the time, I was focused on generating the science that was necessary to answer the questions that we realized were legitimate questions, but for which we didn't have a lot of the answers back then. And I'm proud to say that this book generated a lot of funding, which has generated a wave of science, which allows me to talk with you about what we now know. So I thought that new science would inform policy of government, regulations, laws. And it is, but it's glacially slow. And as I was going around speaking about this book after it was published, I would accept invitations from environmental groups, from universities, and from industry to go and talk to them about, get their reactions as to what they thought of the science. And one night, I was lecturing in Camden, New Jersey to the Society of Plastics Engineers. Not my friends. Any of you know where Camden, New Jersey is? Okay. Well, Camden is, when I was growing up on the East Coast, Camden was famous for being the home of the mob. Where, if they didn't like you, they used what are called cement overshoes to get rid of you. There's a bucket, there's wet cement, they put your feet in the bucket and they throw you in the river. Okay? So there I was, lecturing to the Society of Plastics Engineers on a dark and stormy night with a room full of people who didn't like me. And it was very contentious. I lived through it. Then it was over and everyone left except for 2 big guys who were in the back of the room. And they started to walk towards me, and I'm not kidding, I was physically afraid. They came up to me and they said, Dr. Myers, we like what you're doing. I'm thinking, what? He said, we like what you're doing. You're making certain commodities, plastics, unsellable in the market, and we have the replacement, and we're going to make a lot of money. And I've spent the last 20 years trying to figure out what that means. And I'll talk about it at the end of my talk, where that's led me, because I think that now we are in possession of enough scientific information to move towards a new generation of inherently safer materials. And if we can help chemists do that, we can help them make a lot of money. And that will lead to a market shift in the availability of safer materials much faster than the slow, necessary effort to move regulations and policy forward. Does that make sense? So, how am I doing for time? Anyone? Okay. So, I want to briefly summarize a few of the key major themes of endocrine disruptor research. And I'll present details on 2 of those themes. But briefly, those major themes are EDCs interfere with hormone action, including by changing how genes are being turned on and off. That's central. A second is that hormones act at really low doses, parts per trillion. Well, endocrine disruptors also act at really low levels. There are some results that suggest subpart per trillion effectiveness of certain EDCs, but for the most part it's more parts per billion levels. Nonetheless, it's really low. A third one is what happens in the womb plays out over a lifetime. There's a whole new field of science that's developed from endocrine disruption research and also nutrition research that says what the fetus experiences in the womb may not be manifest until the 4th or 5th generation of that person's life. That complicates the science really a huge amount, and most of it is being worked out through animals, but there are now some cohorts of people where you can ask questions that way. Exposure are ubiquitous, I've said that before. They also are mixtures of exposures, not single chemicals at a time. Every one of us has multiple endocrine disrupting chemicals in us all the time. A complication which I wish I had time to go into, but can't today. Some of these epigenetic changes are inherited without changes in the DNA sequence. That's been the most frightening result for me, the most unexpected result for me in the last 20 years.
Dr. Myers, that's the gene line or is that germ line?
Oh, it's germ line.
It is germ line.
Germ line is what geeks in biology refer to as the sperm and the eggs. Okay, it's what's passed down from generation to generation. A key point is that how we've gone about asking what is safe and what is not has deep flaws. Deep flaws. We're referring to compounds that challenge those assumptions of toxicology as they're neotoxic. They're asking questions that toxicology didn't traditionally ask. And as the Endocrine Society and WHO reported, we now have plausible data linking EDCs to a wide array of compound diseases and disabilities. Lastly, the positive take-home message is we can work with chemists to reduce the likelihood that this moves on into the future. Deploying a new generation of materials is inherently safer. So I'm going to go over two of those points with a little bit more detail. The first one is that interactions with adverse effects take place at really low levels. And I want to focus on atrazine. It's Syngenta's, one of Syngenta's main products. Sold here, not in the EU, and also sold in the US and Canada and lots of other countries. So here are two frogs. They're mating, aren't they? Okay. They were exposed from hatching to metamorphosis when they changed from tadpoles into adult frogs. They were exposed to 2.5 parts per billion in the water for that time period. Everything looks great except when you learn that this is a genetic male and it's grown up as a functional female. It can be fertilized and those eggs are fertile. And the scientist who does this at UC Berkeley has 4 generations of this line of genetic males, about 10% of which are functional females. That was caused by that exposure from hatching to metamorphosis of 10 parts per billion atrazine. So I said there are low levels. Let's think about levels of atrazine. If you're a farmer and you're using atrazine in your cornfield to kill weeds, you want to have about 1 million parts per billion of atrazine on the plants. That's a lot of atrazine, okay? This is a log scale, so that's 1 and that's 100. And that's a million. So if you go and measure atrazine in the environment, what do you find? You find, well, in rivers downstream from where it's being applied, it's about 100 parts per billion. In runoff off of the field, it's about 8,000 parts per billion. Midwest streams, surface water, it's on the order of 80 parts per billion. Rain downwind from the fields, it's on the order of 80 parts per billion. Rain anywhere in the US, it's about 1 part per billion. This stuff, what it does, it evaporates when it's put on the field. What they call it volatilizes. It becomes a gas. It moves into the atmosphere. It gloms onto water, and it's carried. And then it rains, and it comes down. The EPA's short-term safe level of exposure, they calculate to be 100 parts per billion. And for drinking water, they consider about 1.2 parts per billion being safe. Well, the scientist whose work I just showed you has showed lesser effects of atrazine down to 0.1 part per billion. And the result I just showed you is at about 20 parts per billion. So it's a low level of atrazine compared to what you can find in the environment. Okay, so low levels matter. Now I want to talk about that thing where I said where events can last a lifetime, they can play out over a lifetime. And here, I'm sorry it's lunch. This is the inside of a mouse. Okay. These are experiments done at the University of Missouri. And this is a normal male mouse that's my age in mouse years. Okay, so get this is the control mouse. It's got normal kidneys. It's got a normal bladder. It is a male, although that's irrelevant in this experiment. What would have happened if that mouse's mom, during pregnancy, had been exposed to 20 parts per billion of bisphenol A, BPA? What would have happened? And allow him to grow up. to my age and mouse age. Well, the kidneys are no longer working. They're completely necrotic. The bladder literally is about to explode. The animal can't pee anymore. The testes are normal. That animal would have died in the next few days as its bladder exploded if it had been allowed to live. What happened? Well, you think about what's called the urethra, which is what we all pee through. Okay? There is a section of the urethra as it passes through the prostate gland where there were epigenetic changes induced in the tissue, that little section of tissue, so that as the animal aged, key genes in that animal's urethra responded by constricting. And as the older he got, the less and less he could pee until he no longer could pee. That didn't appear until late in the age of this animal. It couldn't have been detected if you tried to measure it, except using really advanced modern epigenetic molecular biology. It couldn't have been detected by the normal things that toxicologists do, weigh things. Okay? So, except for Martin, he does better things than that. Anyway, so you can see here's one very conspicuous example of how things that happen in the womb, mediated by tiny amounts of an endocrine disrupting compound, can play out over the lifetime. Urologists are really excited about this result because it's the first animal model they've ever had of what's called obstructed bladder syndrome, which is increasing in frequency in adult males, humans. They're not at a point of saying whether or not BPA is involved in this in people, but they are now using this as an experimental model where they can set the mouse off on a course of obstructed bladder syndrome and then give it drugs, interfere physically to try and change the course of development of that particular malady. I'll make one point about how the tools we have used to work to figure out what's safe and what's not have failed us. I'm going to show you another mouse picture. This is a control mouse. This is from the experimental group. It's the same strain of mice, the same caloric intake, same activity levels, monitored through the lifetime of the animals, yet one is grotesquely obese. What happened? It was exposed to what are called obesogens, which do what I mentioned earlier, where they change stem cells, they cause stem cells to become fat cells instead of bone cells. Here's why this is misleading for traditional toxicology. It was 1 part of a synthetic estrogen that caused that, 1 part per billion. If that animal had been exposed to a million, to 1,000 parts per billion, much higher level, you might think, oh my God, it'd be that much fatter. Instead, it's thinner than the control mouse. So what happens at high doses can't be used to predict what happens at low doses. Yet all of regulatory toxicology is based upon the assumption that anything that happens at a low dose can easily be detected by using high doses. It doesn't work. Right now, the National Academy of Sciences is in a big review of this whole phenomenon called non-monotonicity. And if it goes the way I think it will, there are going to be major changes in how regulatory toxicology is practiced, and there will be big changes in probably several hundred levels of the ways that several hundred changes in current chemical safety levels, possibly by a factor of 1,000 or more. Big implications. So, what's the next challenge? There's still a lot of science. If you're in science, in this science right now, as a scientist, it's so exciting because we're learning so much. We have the tools that we just dreamed about 20 years ago. Things we can ask things, we can do studies we never thought were possible. But I think we know enough now to begin to incorporate some of this stuff into a new generation of precautionary health principles. Let's let the current regulations and policies reflect what we now know. They don't. I think when they begin to, will help people be healthier. And we can give better design signals to chemistry, green chemistry. We can help those chemists make things that are inherently safer at the beginning. Now, I've been working on this with teams. I organized a team of about 36 people about half chemists, half biologists. Been bringing them together for 5 years in this team to see what would work for the chemists. We had the biology in hand. We knew the molecular stuff. We wanted to design a system that would work for a bench chemist. They're sitting in his lab, or standing in her lab, beginning in the early phases of designing a new chemical to be taken out in the market. We figured, our reasoning was that if we could help them stop wasting time on chemicals that ultimately are going to cause problems, they won't waste money and time on those things. They'll be able to focus on the chemicals that some sort of intellectual framework would help them identify. So it's been a lot of fun. I can tell stories about how you get these two different types of scientists to work together. Here they are learning how to make gourmet appetizers in teams of chemists and biologists, just to get the language going right. So we developed this system, which we call a tiered endocrine disruptor protocol. We're real good at acronyms, right? It's voluntary. This is not, we didn't develop this for the regulatory system. If we had tried to develop for the regulatory system, we would have had a room full of lawyers, and we wouldn't have made any progress. We had a room full of scientists, biologists who wanted to help chemists, and chemists who wanted to help making more money. Very different dynamic. It's also not about current replacements. One of the classic stories in this whole field is how you find out something's bad, you look for a replacement, you look on the chemical shelf and you grab that, well, this looks good, and you stick it in. But the problem is, most of the time we know much more about the chemical we're replacing than the one we have available to replace. And so we stick that one in, and boom, we discover, oops, that's got problems too. And that's been a recurring theme for many decades in using current replacements instead of helping chemists design new chemicals that we know through biological study are much more likely to be inherently safer. It's economically efficient. We're helping, and like I said, we help them not spend money throw money down a rat hole on something ultimately they won't be able to use. Help them figure out early in the process what's likely to be a problem. Key thing here, we're talking about endocrine disrupting chemicals, so you have to structure your experiments, your studies, using principles out of endocrinology. And I could go at length into this. One of the key principles is high doses don't predict low doses. Okay, that's a key principle. And so that's part of the design process of any experiment you would do in this work. And finally, this is designed to, our protocol is designed to evolve as the science develops. Regulatory science gets locked into things so that today, literally today, assays are being used that were invented 50 years ago. It's sort of like, how many of you know who the car guys are in the US? It's a radio show where people call in to figure out how to get their car fixed. It's really funny. It's wonderful. It's kind of like when a person calls into the car guys, the old toxicology, they call in and they say, well, my mechanic wants to weigh my engine to help me figure out how to fix it. Old toxicology spends a lot of time weighing organs, not looking at modern molecular genetics. It doesn't make sense. So we've got this system. It's tiered, which means we have different levels of testing. We use computational methods to the degree that that's possible. We then use cell-based systems, which you can do a lot of very fast and relatively cheaply, to ask how many different hormone systems, how many different hormone receptors is that chemical likely to interact with. We do a more sophisticated look at detailed systems in cells. We then use fish and amphibians. You can't get away from animal testing when you're dealing with hormones, because hormones are a complicated system that works not just across cells, but across organs. And you don't see the full system until you're looking at the whole organism. And finally, you work with mammals. But what happens in your process is this may throw out 30% of the chemicals. So you don't waste money on these more expensive ones. And by the time you get down here, you've got something that's, if it's made through all these systems, it's very likely to make it through this. So by the time you're this far down in the testing, a company is confident, relatively confident, it's worth investing in the time and money necessary to do that final level of testing. We did some thought experiments with this where we tested, using the scientific literature, we took some of the compounds that Mark and I mentioned, BP, atrazine, perfluorine, chlorinated compounds, phthalates, organotins, perchlorate. And we just looked in the literature for tests of these compounds organized as we had organized our testing system. And we found they all got caught by the end of the process. So, we're in field testing right now. This is not an easy, quick answer. There's a lot of green chemistry we don't yet know how to do. But it's a future that takes us away from the gridlock we have now, moves us toward a generation of chemicals that's inherently safer. I think it's an astounding, exciting path, but society is going to have to invest in green chemistry, in the tools of green chemistry, the intellectual tools of green chemistry, to really make this a viable solution. So I leave you with that list. If you think about your friends and your family, everyone in this room knows families who are bearing one or more of these burdens. Everyone in this room. That doesn't have to be. We have the tools now to move away from that reality towards a much healthier future. Thank you.
I guess there would be some questions. Should we maybe agree to start eating a little bit already? And whilst asking a few questions?
Sure.
If you like. Okay. Does anyone have a burning question already? Otherwise, yeah.
Yeah, just a really quick one about Syngenta and atrazine. And I guess Syngenta would also agree that atrazine could be harmful if it's not used in the correct dosage, but if the dosage is correct, then it's not harmful. And you've obviously showed that it could be harmful to frogs at 1 part per billion, but how can we prove that it's harmful to humans as well? I think it's kind of a really difficult
And
question.
that's a great question. And the question is, what level of certainty
Right.
do you want? Atrazine affects estrogen hormones throughout every vertebrate class. Every vertebrate class. Mammals, frogs, fish, birds. We aren't certain that it affects humans. There are human studies that are consistent with an effect. We aren't certain. So here's the question. Imagine you're 30 feet up on a ladder and you fall. Are you going to get hurt? You're certain you're going to get hurt. You aren't certain exactly how it's going to be. Is it going to be your knee? Is it going to be your arm? Is it going to be your head? We can take certainty so far, but we can't take it to the details. Atrazine is affecting human health. Why does Syngenta, at the same time it's producing a chemical that basically what this does is it turns on an enzyme that converts testosterone to estrogen. So it makes for more estrogen. At the same time, they sell a pharmaceutical that turns off that gene to treat breast cancer. So they're saying the effect of having atrazine in people turning on the gene, it doesn't matter, but we use it as a pharmaceutical when it turns off the gene. There's some inconsistencies there.
Right, okay. Yeah, I just think, and I would agree with that, I just think it's difficult to get them to change something if there's kind of no conclusive proof that people right now...
Question of certainty. Atrazine did just settle last year a $105 million lawsuit, which is, I think, one of the reasons why, and that took place in the Midwest where water utilities were being forced to clean up the water supply, the drinking water supply for people, because there's too much atrazine to meet the weak EPA standards. Okay, so Syngenta facing what was probably going to be 100, or at least $1 billion, if they're going all the way through the end, they settle for a $105 million lawsuit, which is probably what got the chief risk officer's attention to write that report.
What is your take on the relatively recent discoveries due to satellite? A take of the swirls that they say 5 swirls in the oceans that are larger than the United States, and whether it's Greenpeace or environmentalists have gone out and they've done just a gross evaluation that these things are 3 to 5 meters in, and they fluctuate. Sometimes you can't see them because of the currents. And much of this is used plastics that are 60, 70 years old.
Yeah.
And they're washing up on shores where there aren't any tourists, but around the world. And it's
Well,
a
so you're-
zillion tons of
Yeah,
plastic.
you're talking about the great plastic patches, garbage patches that have been created by oceanic gyres in multiple oceans. It's a problem, and it goes beyond the physical presence of the plastics and the fact that that's ugly. Turns out those plastics are really good at absorbing persistent organic pollutants and other contaminants that are in the thin surface layer of the ocean. And so they actually turn out to concentrate contaminants that would have been spread relatively thinly onto their surface, and then they're consumed. So it's a way of passing these potential contaminants into the food chain.
All the animals in the oceans are feeding off this stuff.
That's right.
And
Yeah.
they've done biopsies, so every animal, and they've found traces.
So I wasn't exaggerating when I said every living organism.
No, they've done polar bears and whales and sharks and
Yeah.
ducks and everything that's in the ocean. From the internet, 98% of man's garbage goes directly or indirectly
Yeah,
in the ocean.
That's not my, I don't know those numbers.
I know.
Yeah,
But
but it's a lot.
yeah.
It's a big number.
And if you're going to do anything, that has to be stopped one day.
Yeah.
It can't continue. It's continuing now. And the other thing is, what's your take on fracking and all the chemicals that are being pumped? I looked at the list once, and I'm in the medical world.
Right.
And 1/3 of those are benzene and all these.
Yeah, and actually there will be a study coming out in the near future saying that some of those chemicals are endocrine disrupting chemicals. And if you go to Colorado in
Yes.
the West,
I have a friend in Colorado tell
Okay.
me this.
and these are areas where you never even used to bother to measure ozone. Never bothered to measure it. All of a sudden, some people discovered, wait a second, we got high ozone levels in rural Colorado. And it's because of the volatilization of the fracking chemicals from these ponds that they have, putting rural Colorado, out of ozone attainment. It's ridiculous. We had a question back there?
Yeah. Atrazine is a triazine, isn't it? So,
Yes.
would you expect the same endocrine effects from other triazines, or is it specific to atrazine?
Well, they haven't, to my knowledge, no one's looked at other triazines in that regard. It's plausible that they have similar effects, but they're different triazines, and their molecular structure will be important in determining what receptors they can affect. So I don't know the details of those others. I haven't seen comparable studies done. I think they should be looked at. But it may be there's something unique about a particular other triazine that means it can't interact with aromatase, which is the gene that's disrupted by atrazine. Yeah.
Thank you so much for your help. When you're designing the near chemicals, what do you look for?
Well, first of all, a chemist has to have in mind, what am I trying to make a product to do? So they've got in mind certain material characteristics they want to achieve because they know they can get a market for it. So maybe a BPA replacement. Then what our system does is it systematically tests using initially relatively cheap, fast assays. Does it bind with the estrogen receptor? Does it interfere with aromatase? Does it, there are 48 nuclear receptors in vertebrates that all of which are potential targets for endocrine disruptors. So we systematically try and figure out, is this compound interfering with one of those? And if it is, we can tell the chemist one of two things. Well, first of all, replicate with a different system. Because science always needs replication. Second, if it's replicated, then maybe you ought to not use it. But there's a third alternative, which is, let's say it's a really cool molecule that's got just the characteristics you want. And chemists can now do this. Not all the time, but there's really fascinating work. They can alter the molecular structure of that molecule in a way that it maintains the material characteristics they want, but somehow makes it impossible for that molecule to bind with a receptor. So that's the holy grail in this. We help them not just eliminate compounds, but do engage in molecular design so that they get what they need without it being hazardous. But we are a long ways from operationalizing that.
Got a four-part question for you.
A four-part?
Yeah.
I'm jet lagged. I have to remember every one of them.
Sorry. So just thinking back up like the industrial side, what's the common defense for these arguments by the Syngentas of the world, and kind of what's the best way of diffusing that? Secondly, in your work on the protocols, have you started to engage with industry in any way to kind of mainstream the thinking?
Yes. We even have been in contact with a relatively progressive unit within Dow.
Yeah, great. And then third, have you started to also engage with graduate schools of chemistry to integrate this into the talk curriculum so that, as you showed in that diagram, like the first stage of a chemist's mindset isn't design material characteristics, but rather design material characteristics that aren't going to shoot ourselves in the foot. And then lastly, just a very practical question. Have you changed the way you live your life having discovered these things?
Yes. And let me, there were two questions that were more complicated. So let me do the training question first. Some of the chemists on our team are really big into reforming the training process for PhD chemists. You can Google a guy named Terrence Collins, runs the Green Chemistry Institute at Carnegie Mellon University. He's one of the best people working at molecular redesign, does fabulous stuff. He's got an awesome website. He teaches courses about sustainability, which this is a central part for his students. He makes his students read Our Stolen Future. These are chemistry PhDs. They have to read Our Stolen Future. There's another part of the team, another chemist named John Warner, who actually was the co-author of the founding book of green chemistry, Chemistry Principles, and I forget the full title, along with Paul Anastas. And John has formed a nationwide consortium of people teaching at multiple levels, teaching chemistry at multiple levels. It's called the Green Chemistry Challenge. And their focus is to introduce questions like this early in the training of new chemists. It's not very popular in some circles because, like all academic disciplines in universities, they're very siloed, they're very traditional. They don't change easily. But we think this one has the chance to change because John Warner, who doesn't teach now but did teach for 12 years at the University of Massachusetts, John had the only training program for green chemists when he started. His chemists, his graduates, had an average time from graduation to employment of 3 days. Companies want these skills. The longest was 3 weeks because she had 3 offers and couldn't decide. Companies want the skills. There's a growing cadre. There's several different national organizations, national efforts to get green chemistry into the core curriculum. UC Berkeley has one. University of Oregon has one. John's work in New England. So it is underway. Never fast enough, but it's, and actually we have, for the last 6 years, we've taught at a national chemistry conference with 21st century toxicology every chemist should know. And it's standing room only. We're brought back every year. And it turns out a lot of people who are in other areas of science think that toxicology is really boring. Regulatory toxicology is not very interesting scientifically. But if you bring in the people doing this type of research, which is elegant and based on modern molecular genetics, you can get people, other disciplines, really excited about it. So every year we bring in world leaders in epigenetics, world leaders in endocrine disruption, world leaders in all these, and it's inspiring. The first one about what do people say? How do companies react? Well, let me recommend a couple of books because there's a big literature on this. It's called Manufacturing Doubt. I I mentioned BPA gets $700,000 an hour in revenue, and it pays for a lot of manufactured doubt. Companies, and I work with some companies that I'm using the phrase too much as a catch-all. They're really good people in lots of places. But if you read Naomi Oreskes' book called Merchants of Doubt, thank you. What she does is she traces the movement of manufactured doubt, a process of raising enough questions that a regulator is not willing to make a decision, and that's where a regulator likes to be. So he can say to the science, come back to me when you make up your minds. So the manufacturing doubt is throwing enough doubt into the thought process of a regulator so they won't make a decision. Naomi Oreskes in this book, along with Rick Conway, shows how people that initially were involved in the production of the nuclear weapons then got drafted into the defense of tobacco, then became involved in manufacturing doubt on chemicals. Many of them are the same people. I know this may sound implausible, but you need to look at this book, Merchants of Doubt. And there are at least three other books that are vital to this whole, understanding this whole process. One is Doubt is Their Product by the current head of the Occupational Safety and Health Administration in Washington, David Michaels. And then a series of books by two historians of science based in New York City, Jerry Markowitz and I'm blanking on the other author's name, but where they trace, specifically within the chemical industry, the history of the lead industry, some of the compounds I've been talking about, and they show how doubt has been persistently manufactured. And there are some pretty standard tools. They say, oh, all those experiments by animals are with high doses, so they're irrelevant to people. Okay. Well, that's not true, but it's an easy thing to say. They say animals aren't little people. Well, that's true. There's some differences, but we also share a lot in common. There's a series of standard responses that are part of the process of manufacturing doubt. Yeah.
I guess you're hungry. Let's not be unfair. Maybe if I might close just with two brief questions. First of all, this being a financial hub, what is your recommendation for investors? We have some analysts here that actually have to make recommendations for, investors in stock. What is your recommendation there? Maybe some companies that are leaders or laggards. And also secondly, maybe the last question, what can an individual do? What you showed us is quite scaring for me as an individual. What can I do to reduce my exposure?
Well, if you find a copy of Our Still in the Future, there's a whole chapter on protecting ourselves, the things individuals can do. There's a much more recent book called Slow Death by Rubber Duck. And the reason why they focus on the rubber duck is because a rubber duck, those yellow things that you squeeze, the reason why you can squeeze them is because while they're made of polyvinyl chloride, which is a hard plastic, you put a lot of phthalate in it, and that makes it flexible. Okay? So Slow Death by Rubber Duck is an experiment of two guys in their 40s who commandeered their mother-in-law's apartment and lived in it for a week. And during that week, they did two types of experiments. They weren't pregnant because they're guys. They were in their 40s, so they weren't developing. And so they set out to manipulate their exposures, increase them and decrease them, and see if they could do something. And it turns out BPA, you can change your levels a lot by avoiding some of the things I mentioned. Phthalates, you can change a lot. Triclosan, you can change a lot by making different consumer choices. Perfluorinated compounds you can't because they're very persistent. So how much you can do is going to depend upon what are the characteristics of the compound that you're working with. The problem is, so what mom is going to have the time to spend making those choices and have the knowledge to make those choices? I don't think mothers should have to be a chemical engineer to go shopping for their kids, right? That's not fair. They've got big things they have to worry about in their daily life. So that means society has to step in and do things too, right? So that's, I could go off on that for a long time. But in terms of investments, there are actually, you've written about Pam Marone's work with green pesticides.
That's right, biopesticides.
Right. That's an interesting play that's available in the market today. I actually know Pam because she's participated in some of our meetings. Yes, and we did some research on it. Found out what you there are some plays like that. The big plays are in the future, unfortunately. I think the most interesting one right now is actually by Terry Collins. Now, I mentioned Terry. He's at Carnegie Mellon University, and what he's done with over 20 years of intensive chemical research, manipulating the shape of a molecule, testing it, seeing how well it does in cleaning up chemicals out of sewage water. Doesn't work quite well, he changes the molecular structure until it works a little bit better. Tests it again. Figures out what part of the structure is now the rate limiting factor, changes it again. Over 20 years, this constant pattern of test, change, test, change, test, change. And now he's going to scale in Europe, in the UK, in water treatment systems. They're doing full-scale experiments, because I don't know about Switzerland, but in the UK, wherever you take your, UK takes its drinking water out of the rivers, right? And there's always someone living upstream and someone peeing upstream, okay? And that means, and the current sewage treatment systems do not take estrogens out of water. They don't. They don't take a whole bunch of stuff out of water. And so, as that stuff is coming downstream and this town takes it out, puts it through its sewage treatment system, puts it back in, and this town does, there's a huge public health incentive to try and get those sewage treatment systems to work better. And Terry's molecule, called Tamil activator, and I don't know enough chemistry to explain it to you, but am I supposed to stop? It's reaching the point where it's going to be a really interesting investment. Okay, thank you.
Thank you very much.